Welcome to GeomaCan, the podcast where we explore the story behind the technological innovation and discuss what geomatics can do and make. I'm Abdelrazak Robi, your host, and I'm thrilled to have Geoffrey Jacobs with us today. Geoffrey, thank you for accepting our invitation to share your experience, your journey into the early days of 3D laser scanning with Cyra technology is incredibly fascinating, and we are excited to learn from your insight.
Thank you very much for the invitation, Karubi.
So, before we dive into details, Geoffrey, I want to acknowledge that you are, when I did my research, one of the person I found were in the first day of laser scanning, in the infancy of 3D laser scanning, mainly in the marketing part. So being apart from technology, from Cyra Technology, which is a company, a startup company that was in the front of developing the first 3D laser scanner. Let's start our conversation here. Can you take us back to this early day and share what initially sparked your interest in this technology at Cyra Technology Company?
Sure, it's my pleasure to do that. I think going back to the early days and the question of what sparked my interest in 3D laser scanning, there were really a couple of aspects to it. The Cyra Technologies was founded in 1993, right? But they didn't start to sell actual products, a scanner and software, until 1998, right? I was first exposed to them in 1996, so it was 2 years before they actually started to sell products. And at the time, I was working for Trimble. Trimble Navigation. Trimble was, at that time, the headquarters for Trimble, where it was in Sunnyvale, California, which was in the heart of Silicon Valley in the San Francisco Bay Area. Cyra Technologies was a startup company, as you mentioned, and it was also happened to be based in the San Francisco Bay Area. Okay. It was a very small company, but they had a very big vision for the technology. So even though it was a small startup, they had big ideas for it. They thought the founder, Ben Kacyra, he thought this could be a big thing, and he really didn't want to pursue it unless it was going to be a big thing. So since Cyra was a very small startup company, and he had big visions for it, as the technology was being developed, he wanted to identify and see if he could connect with what he called big strategic partners, right? Some big company that he could partner with that could help him commercialize the technology globally, right? And Ben Kacyra himself, he had a background in education in civil engineering and had also taken surveying as a course. His father was in the construction industry, so Ben was familiar with surveying, and he thought as the technology was being developed, he had envisioned that maybe one day it could be a surveyor's tool, right? So he asked some surveyors in the area where he lived and worked. He asked them, if he was going to approach a big company to try to take this technology and commercialize it, help him commercialize it, what is a very innovative technology, what company would they recommend to approach? And they all said the same thing. They all said, you should talk with Trimble. Okay. And why Trimble? The reason was an interesting one. Was Trimble was actually founded. The founder of Trimble is Charlie Trimble, and he used to work at Hewlett Packard. He was an electronics engineer at Hewlett Packard, and he left the company and he left Hewlett Packard. Very smart guy, and developed his first products were actually LORAN-based systems for navigation, for aircraft navigation and marine navigation. And then at one point he was able to get some GPS technology that had been developed at Hewlett Packard and buy the rights to it. Hewlett Packard thought that GPS was never going to be a big thing, and they wanted to get out of it. So Charlie Trimble bought GPS, and to make a long story short, Trimble basically became a GPS company. They were the first company to really commercialize GPS from a consumer standpoint or from a user standpoint.
At that point, Trimble was not selling, for example, device EDM, electronic device measurement, distance measurement. No,
that's exactly right. So at that point in time, this was 1996. Trimble was a GPS only company. They had a lot of different GPS types of products. One of the product areas that they had was they had commercialized and developed the use of GPS for surveying. And they had GPS receivers that were used by surveyors. And it turned out in Trimble's overall business, the surveying products were the ones that were the biggest revenue and the most profitable by far. And they were so successful in that area that the company decided to expand. This was a very confidential and strategic decision within Trimble. They decided that they want to expand outside of GPS and add traditional EDM type technologies and compete overall in the surveying market. Not with just GPS, but with all products, right? So this was a very confidential strategic decision, and actually they were developing their own total station, a specialized total station at that time. Never wound up going to the market. And eventually Trimble merged with a company called Spectra, and that's how they got a broader portfolio. But at the time, it was like Trimble wanted to expand into traditional EDM based products. So at the point in time when Ben Kacyra approached Trimble, I was the director of product marketing, product management for the GPS receivers for surveying, and that inquiry landed on my desk. So one of the reasons I was interested in it was I knew that Trimble wanted to expand outside of GPS, right? Nobody else knew that, but I knew it, okay? And I didn't tell Ben Kacyra that either. I just said, okay, I'm interested. So one part was just the timing happened to coincide with Trimble's interest in expanding outside of GPS, right? And the second thing was, that sparked my interest was I started to evaluate technology that Cyra had, and also the company, right? So if you're going to partner with a company like any company, you evaluate, well, what's the technology that they're developing, and what about this little company, right? So I wound up having lunches with Ben Kacyra over a long period of time, and he was pretty secretive about the technology, but it finally reached a point where I was invited to their offices. The offices were in a small business building in Orinda, California, which is in the same town where Ben Kacyra lived, right? And invited me over for a demo. So I went and saw the demo, and the demo was held in a conference room. It was a small conference room. And they set up this scanner on one end and of the conference room, and on the other end there was a dartboard on the wall, and it was a dartboard like with the little wires on the outside, and to clearly mark, the divisions of the dartboard. And then they started to scan the dartboard, and I could see that it had a visible green laser, and it moved in vertical columns. So it would move down one column, down the next column, and then move from left to right as I was looking at it, and I could see it scan over the dartboard. And as it was scanning, the points would be displayed on a laptop. And so I was watching the scan on the wall, in
real time.
In real time.
Oh.
Yes, in real time, right. I'm watching it scan on the wall, and then I'm watching these points start to display on the laptop, right? And then about halfway through across the dartboard scan, and this was scanning at, let's say, a few hundred points per second, so it was not, wasn't nearly as fast as today's scanners. I'm watching this, and then the operator at the laptop that was controlling the scanner and displaying the points started to rotate the image that was on the screen in 3D and zoom in, pan back, and rotate it in 3D. And my jaw dropped, okay, because I had never seen anything like this before. And then, so they completed the scan, right? And they did a treatment where they turned the points that had been captured into different colors, this color mapping basically. And you could read the numbers on the dartboard. You could see the divisions very clearly. You could see,
how much it took to scan.
How long did that take? It took a few minutes, the whole thing. It didn't take that long, maybe 10 minutes, 5 to 10 minutes at the most, maybe 5 minutes or so. And I was just blown away. I thought, wow, this is really something. I had never seen it. Again, I was living and working in Silicon Valley, and this was in the 1990s. And so there's technology explosion of all kinds of cool technology in that area. But I had never seen anything like that before, right? So I just thought, okay, this is pretty cool stuff, all right? So that was the demo had a big impact on me in terms of sparking my interest. But then the second part was, okay, well, what about this company, Cyra, right? Are they a good company to consider partnering with, right? And so I had, early in my career, I had attended a business development course, seminar for a few days on identifying, evaluating, commercializing new technologies, right? By education, my background is I'm an engineer. I have a Bachelor of Science in Chemical Engineering and a Master's of Science in Chemical Engineering. So I understand technology, right? And I had always been interested in commercializing new technology as a sort of a career passion. So I'd taken this course, and one of the keys out of the course, I learned a lot of different things about what to look for. And number one was that 9 out of 10 products that are successfully commercialized are based on a clear market need, right? So I was curious about, well, why was this technology being developed? And I asked Ben Kacyra that, and he was very happy to share why that was. Ben had, again, he was an engineer himself, a civil structural engineer, and he had founded an engineering design consulting company in the San Francisco Bay Area, built it up over many years. It's very successful. And one of the areas that he was involved, he provided services for, was to provide design work for modifications to nuclear power plants in California. So California is in a seismically active area. And at some point, and this is in the 1980s, they figured out that building these nuclear power plants along fault lines was maybe not such a great idea. So there was a lot of a lot of activity in what was called seismic retrofits. It's where they had to make modifications to the nuclear power plants to be able to withstand earthquakes, right? And his company was involved in designing those modifications to the nuclear power plants. And in order to design a modification to a plant, or what's referred to as a revamp or a retrofit, you have to start with, well, what's already there, right? You have to know what's there so you can design modifications to it, and design, if you're going to put new things in, you have to route piping or put in new structures. You have
the
to
retrofit design.
Yes, right. And you start out with what's referred to as an as-built. Okay, you need a very accurate drawings of the way that power plant was built, not the way it was designed, because sometimes construction works out a little different than design. You need to know what physically is there, right? So part of his service was going out, and before you can do the retrofit design, you have to have an accurate as-built of the facility. So he would send out a team of technicians and engineers to the nuclear power plant, and you can only have a very limited time window when you can get in there to do that. It's usually during a shutdown. So he'd send his team in there to do the as-built, and they would collect the information manually. So get on ladders and they climb up, and they would have tape measures and clipboards and notepads, and as they climb up the ladder and take a measurement, they would make sketches.
And at that time, there was total station or not yet? There was total station to make measurement.
There was, right.
And
you would need to use a reflectorless total station, but it's not that easy to use, right, for piping, right? Yeah, I mean, well, you could put targets up there, right?
Yeah, okay.
But these are very complex piping systems and steel structures, and that was just not, you can't have visual access to that stuff that easy. So his teams would collect the as-built information manually, right? And it turned out there were safety risks in that, right? Because they're climbing up ladders with a clipboard and pencil and a tape measure, and they would make sketches. And the big problem was that, so you could use that information. They create their as-built drawings, and then they go back, they make their design for the retrofit, and then it goes into construction. The big problem was there were a lot of the as-built measurement method was it was prone to error, right? Both in measurement error and sketchings. They might sketch something and that would go in the wrong direction. They might not get everything that needed to be captured. And if you use that information to make a design, it goes into construction. When you go into the field, things don't necessarily fit up, right? Or you may have what they refer to as clashes, right? You're out of pipe and it runs right into a steel beam, right? Or there's things that you just didn't account for accurately in the as-built. So and it was a very tedious process. Took a lot of time and labor in the field. It was challenging to do it within the time windows that were available during a nuclear plant shutdown. And then it was sometimes problematic in the office to try to do the designs. This was at a time in the late 80s where CAD had just kind of been commercialized and come into being. So it was good for drafting. And in fact, that's one of the things that inspired Ben Kacyra. He said, CAD has helped to automate the design and drafting process, but we're still doing these as-builts on these plants manually. And Ben being, Ben, a visionary type of a guy, entrepreneur, they said, there's got to be a better way to do this. There's got to be a better way. Well, we've got CAD now in the office to automate the design and drafting. Right, what we're still doing is, as-built manually, and it's fraught with error and problems. there's got to be a better way. And that was the need that sparked his interest in trying to figure out a better way. And that's why he started to go ahead and he teamed with a consultant that he had, Dr. Jerry Dimsdale from University of California at Berkeley, this guy was a consultant doing other stuff. And they decided to start a project or a little company to try to develop something to solve this problem. An automated tool. Again, Ben had a background in surveying, and he thought, wow, if we could develop some kind of a surveying tool to do this automatically, that would be great. Right? So back to the question about what sparked my interest, this was being developed based on his understanding of a very clear need in the market.
Yes.
And for me, that was a big check mark, my evaluation, right?
And it was Cyra who asked to join Trimble so they can, for example, manufacture more laser scanner, distribute, and
Right.
Yes.
A global distribution, a big manufacturing company, right? To develop, yeah, exactly. That was what his vision was. They were, again, Cyra was a very small startup. When I joined there in 1998, I was employee number 20. Okay, and I was the first real marketing guy, right? So another factor for me, and when I was evaluating Cyra, is like, okay, the market need was clear. I didn't know how big the market was, but it was clearly being developed for a specific market need for these industrial plant retrofits. And Ben is, for those who've never met Ben, he has infectious enthusiasm. He's one of these people, when you meet him, they're so enthusiastic about what they're doing, it really helps you believe that this is a really good thing, right? And I think everybody's run into somebody like that at some point in time. Ben also had a very good track record. He had started up other businesses. He started up, it's called Cygna Engineering, Cygna Engineering, developed to a big engineering company, hundreds of employees. He had lots of different new ventures within that company. And then he sold it off at one point to a company called Kacyra Engineers, based in Oakland, California, which is also San Francisco Bay Area. So he had a good track record of developing, successful businesses. So that was a big plus. Also, over the time that I wound up talking to him for over a period of 2 years while I was still at Trimble, and I was sort of following their development over time. And over time, they started to get some alpha and beta customers to try out the technology. It was very confidential. But those companies were big names. One of them was Chevron, world-class oil and gas company, energy company. Another was the United States Navy. They were interested in it, the technology. Another was a company called Raytheon Engineers and Constructors, which is a big engineering company focused on power plants. Another was a company called Fluor Daniel Corporation, which is now Fluor Corporation. It's a world-class engineering and construction company. Does a lot of industrial plant stuff. So he had developed alpha and beta customers that were world-class. I mean, this was, these were big. That added a lot of legitimacy to the company as well. And then another key for me was the staff, the quality of the staff. Almost all the staff had come one way or another from the University of California at Berkeley, which is one of the world's great engineering, science and engineering universities. If anybody's seen the movie Oppenheimer, many of the scientists on the Manhattan Project came from the University of California at Berkeley. Right? There's the Lawrence Berkeley Labs is there, and that's named after Lawrence, who was featured in the movie. So they had high, good technology, good, smart guys, smart team with the company, and they had also secured a good proprietary position, so to prevent other, companies from just basically doing the same thing, exactly the same thing. They had, and I'll get into this in a little bit, but they had an exclusive arrangement with some technology that they had acquired by way of Massachusetts Institute of Technology, MIT's Lincoln Labs, which does a lot of research for the U.S. government. They had some exclusive technology that they had been able to secure from Los Alamos National Labs. Again, Los Alamos. Again, if you've seen Oppenheimer, you know the quality of the technologists that are at these institutions, right? You got MIT, Berkeley, California, University of California, and Los Alamos Technology, and they had won an award from a very prestigious award called the R&D, Research and Development 100 Award, for the development of this technology. They won it in conjunction with MIT, and if you look at the R&D 100 winners over the decades that award's been, you'll recognize some major technology advances in there. So they had a lot of things on my checklist for being checked off as positives, right? So between the dartboard demo, Trimble's interest in expanding beyond GPS, and a lot of these positives about Cyra, I became very interested.
Yes, by the technology and also by the clear need for this technology. And
Right.
I think this is what makes Cyra one of the pioneer of this technology, because I think the laser technology is very old, the 60s. And I think also the laser profiling, not laser scanner, as we know today,
Yeah.
they were here in the end of 80s.
Yes.
Yes.
Yeah, that's
So
true. That's right. That's true. That's a good point. Is that the laser, the profiling application of it had been there. The, but not the application of that technology for capturing as-built of plans, right?
yes.
That was the one that really drove Ben, and it was based on his experience, from his engineering company. They were out doing this stuff, and like I say, the CAD had already come around. It was a big deal, and so the office side of it had become automated, but the field side was still manual. He said, "There's got to be a better way."
And from the demo that you had in Cyra, do you remember the specification of this first Cyrax 2014 400? Yes, it is the Cyrax.
Yeah, it was called the
2000.
Cyrax. Yeah, the we used to pronounce the Cyrax. It was the Cyrax 2400, right? The Cyrax 2400, and I was the one that was responsible for creating the first data sheet for it. The scan speed spec was 800 points per second, right?
How much? Sorry, how much?
800.
Not a lot. 800.
800 points per second, right? So, if you think about it in comparison to today's scanners, that's several 100,000 points a second, 1 million points a second, 2 million points. You say 800 points a second. Oh my God, that's nothing. But at the time, 800 points a second, there was no other laser scanners, right? Well, there were. We can talk about that later. But the comparison was versus a total station. And a total station could do 1 point maybe every 2 seconds, right? So maybe 1 point a second or 1 point every 2 seconds, you could take a measurement with a total station, right? So 800 points a second at that time seemed blazingly fast, the original spec, right? The original first scanner, right? Yeah, so, but that was it. That was the first scanner, first spec was 800 points per second, and that was considered really fast.
And what about the field of view? I think it was a limited field of
Field
view.
of view, yeah, okay. So we're gonna get, yeah. So the field of it, so it was basically it was like a camera. It was set up like a single shot camera, right? And so the field of view for the first scanner was 40 degrees vertical and 40 degrees horizontal, right? So essentially the field of view of a static camera shot, right? But it was configured on a pan and tilt tripod. So you could take a scan and then move the scan head. You could rotate it up or you could rotate it sideways. You could rotate it up and down, and you could rotate it side to side. And then you would take another scan and you would, take scans to cover the area that you needed to cover, right? Or the space that you needed to cover. So you take a lot of scans. Well, it took quite a few separate scans to scan an area, right? And we'll get into more of it, but it also maybe it's best to kind of talk about some of these key challenges.
What are those challenges and how did you overcome them? And your
Right.
team, of course.
Right. So we just talked about sort of this vision that Ben Kacyra had for solving the as-built data collection problem, right? And so he had firsthand experience in collecting as-builts and doing retrofit design work for these power plant retrofits. So he had an idea of how to spec that, right? There were three challenges. So when I joined the company, it was 1998, and the products were ready to sell, right? So the main technology challenges they had been faced and conquered, if you will, before I got there, right? There were other ones that were developed and improvements made after I got there, but the ones the biggest ones were done before I got there. I became familiar with what those were, and I've learned about how they accomplished them. There were three challenges. One was developing the hardware, the scanner itself. How do you develop a scanner, right? That can meet the specs that Ben had set out. I'll talk about those in a second. The second one was on the software side. Turned out, scanner collects a lot more points than a total station does, right? And the software to manage that turned out to be, that was a big challenge in itself. Third part was the funding, just getting money to support the development of that, right? I'll get into it, but it turned out to be a much bigger development task than what Ben had originally envisioned, right? So there were three parts: one, the hardware challenge, the software challenge, and the money, the funding challenge. First on the hardware, right? The big challenges in developing the hardware to address this as-built problem were in the original specs that Ben Kacyra gave to his chief technology officer, Jerry Dimsdale. He wanted something that was fast and automated. Again, there was this comparison with CAD that had been developed to automate drafting, right? He wanted something fast in the field, right? It needed to be portable. It needed to be basically remote sensing. He didn't want people having to climb ladders, right? And it needed to be able to capture geometry was overhead, so he wanted to be remote sensing. It needed to be affordable. Again, he had the vision of it being a survey instrument one day, right? It needed to be eye safe, right? It needed to be safe to use in nuclear power plants, right? And the tough one was his original spec was he wanted 1 millimeter accuracy at 100-meter range, right? This was Ben just saying, okay, this is ideal. This is what we really want, right? And it turned out that of all those requirements, the portability turned out to be a big challenge, right? But the biggest challenge was the accuracy at range. This 1 millimeter accuracy at a range of 100 meters, right? And why did he need something that was that accurate? Well, it turns out that if you're doing a retrofit to an industrial plant, power plant, one of the biggest challenges, you may have to route new piping into an existing valve, right? Or into an existing point, right? And that's referred to as a tie point. It's where a pipe ties into another pipe, into a valve, right? And especially for what's referred to as large bore piping, which is big, large diameter piping, if you're a little bit off and it comes to that valve and if you're off, if you're too far off, and then they have to do what's called a field fit up. You have to try to fit that thing up, even though it doesn't line up exactly. You have to try to fit it up in the field. It's very difficult. It's very expensive, and it can be the kind of thing where you have to kind of go back to the drawing boards and redesign it so that it does fit, right? So that tie point accuracy is in the order of millimeters. It has to line up. If you have very small bore piping, you can bend the pipe a little bit. Big piping, you can't do that, right? Big piping, it's expensive stuff. So that was the source of these high accuracy requirements. Over time, they wound up relaxing that requirement to 6 millimeter accuracy at 50 meter range. And that was sort of due to the practical constraints of the technology, okay? Ben's original idea, his proposal to Jerry Dimsdale was, I think we should be able to find some off-the-shelf parts, spend maybe $70,000, and we'll put together maybe in 6 months to get to a prototype, to get to this device that can do the things that I want it to do. That was his original vision, right? It wound up taking over 3 years and over $2 million. Okay. Ben said that if he knew that at the time, he probably never would have done it. He says, but that's the way that these breakthroughs happen, right? You start down this path, and then you think, well, okay, well, that's harder than what we thought, but let's keep going, right? Well, and I think probably in your PhD research program, you run into the same things. This is hard, but let's keep going. So absolutely at the top of the pyramid in terms of the development was this Dr. Jerry Dimsdale. Again, he had been a consultant to Ben Kacyra with Ben's engineering company. Jerry was the head of what's known as the Earthquake Engineering Laboratory at the University of California at Berkeley. So Berkeley has a facility where they have basically a small building set on a shaker table. Okay, so they actually, again, this is in California. When there's earthquake, there's faults all over California, and they've had big earthquakes in California, right? So Berkeley has its own earthquake engineering lab, and Jerry was the head of that lab. He's a PhD mathematician and engineer, and he is brilliant. I've had a good fortune to work with a lot of really smart people in my career. He's right there. I mean, he is a brilliant guy. So he was tasked with trying to find these off-the-shelf parts that can make this, unit, right? And it turned out that Jerry also had some firsthand experience with as-built problems because he'd done a modification to his facility, and he had all his hydraulic piping because it's this building on a shaker table, right? And he already had to do this design retrofit stuff, and he knew it was a hard, he understood the pain of trying to do that, right?
Yeah.
He understood the problem, right? So he quickly discovered that this off-the-shelf parts to do this thing there's no way, there was nothing that was even close. There was no way you could meet that accuracy and range challenge, right? He started to focus on what he called radar type technologies, especially laser radars. There were some commercially available products, but they were sort of 5 to 10 centimeter resolution, nothing in the range that Ben really needed. And the equipment to do that was gigantic, right? It was nothing that could be miniaturized, to what was needed. So, it's like, what do you do when you discover that? So, again, this was the San Francisco Bay Area, and there's some world-class universities near there. So, engineering companies and a lot of companies will use universities, experts, and they'll consult with them, right? So they visited this Dr. Robert Beyer, who was at Stanford University, right? Stanford's also in the heart of Silicon Valley. It's in Palo Alto, California, where Hewlett Packard is. And he was known as the Laser King, right? So they visited him and they said, look, here's what we want to do. Is there anything that, you're aware of that could help us do that? He says, well, nothing that you want to do violates the laws of physics. He says, but you're definitely pushing the envelope. He says, and he referred Ben and Jerry to MIT. He says, you need to talk to this guy, Dr. John Zahowski at MIT's Lincoln Labs. He said, that's the guy you should talk to. He's one that may be closest to what you need. And so they visited him, and he said, I have your laser. He says, I have your laser emitter. Okay, I have it. It's this pulsed microchip that had been developed for defense programs. It had a short, high energy pulse, low power, and it was fast. It would do 1,000 points a second up to a couple thousand points a second. Okay. It turns out that he was also an expert in, this is sort of underplayed in the world of laser scanning, right? But is what's called the transceiver and the optics aspect of it, which is the optics takes the beam from a laser and it collimates it into a smaller beam. And you need if you're going to detect edges and around piping and steel edges, you need a small beam. Okay, a big beam you get to scatter. Anybody that's done scanning knows when you get to the edges, the points fly off into space, right? Big beam just makes the problem 10 times worse, right? You need a small beam. So he was an expert in collimating a beam, and then you have to detect the return. You have to time it, right? So that's the transceiver, the receiving part, the transceiver part of a laser scanner. So you got the emit it, you got the laser emitter, you focus the beam, and then you got to receive the signal and time it, right? And he was this Dr. Zahowski was an expert in all that stuff. So for Jerry Dimsdale, all of this stuff was totally new. He didn't know anything about lasers beforehand, and this was all new. So it turned out that they developed a contract with MIT, and they sent Jerry to MIT for 6 months. Okay, and his goal was to come back with a working bench scale prototype, okay, of something that could do what they needed, including the scanning mechanics, which Jerry developed on his own. Okay, and that's what he did. He went there and he developed and he learned and all this stuff, and he developed a prototype. In the process, then Kacyra got a second contract with MIT, which was a $750,000 investment in Cyra by MIT. That was the first investment outside of friends and family. Okay, and as an aside, MIT wound up tripling their investment once Cyra went public. So that was a good thing. And during that time, also wound up revising the spec. So Jerry went there, okay, and he had this thing developed, came back. He says, but there was a problem, and that was the size of the transceiver. It was a rack-mounted unit. There was this big rack-mounted unit, okay? So it was obviously too large to be portable. Right? So they had solved part of the challenge, but how do you get it to be portable? And there was only one way to do that. They needed small, what I'm going to call picosecond level timing circuits, electronics timing circuits, right? I looked around, and as it turned out, that technology had been developed at Los Alamos National Labs. Again, this is the Manhattan Project location, right? There's a lot of sophisticated stuff. That technology had been developed there, but it had never been used, and the project had been shelved. Like, oh great, what are we going to do, right? So what Jerry did was he found the guy who had developed this. The guy had retired, right? He found the guy, and they convinced him to come to California, to Orinda, to develop this, small version of this transceiver, the electronics of it, small transceiver circuit for Cyra. And over a period of several months, he did it. Okay, developed something small and specific for Cyra. Okay. The first iteration was not fast enough to meet it was like on the order of about 50 picoseconds, which was not fast enough to meet the accuracy spec. Again, this is the accuracy spec in range was the big challenge. But then they added a bunch of isolators, and they got it down to around 5 picoseconds, and that was it. Okay, so that with the other combined with the laser emitter and transceiver and the scanning mechanism, that was their first working prototype. That was the first working prototype, and now it's like, okay, we got to demonstrate this for. They had a big demo lined up with Chevron. Now, it turns out, again, the headquarters for Chevron Corporation is in the San Francisco Bay Area. Okay, so and they have refineries in the San Francisco Bay Area. So they went over. They went over for a demo, and the whole thing wound up. The unit that was used, the system that was used, fit in the back of a big van. Took this van over because it wasn't packaged up yet. It was just, kind of a working prototype. Took the van over to the refinery. Vice chairman of the Chevron was there for the demo. They scanned this big tank and supporting steel structures, and they went back to the office and they created a 3D model of it. They showed it to the Chevron vice chairman, and he said, "This is it. We want this stuff." Okay, so they made a $500,000 investment in Cyra. Okay, they decided, and their investment was, we'll buy first couple of scanners for $500,000. Okay. So remember, funding was a big challenge. So they got money from MIT, they got money from Chevron. As soon as Chevron said they were in, then Floor Daniel Corporation said, we want that too. So they bought it. They again they made an investment for about $500,000 for a first couple of scanners. Because Floor Daniel did a lot of the design construction work for Chevron, right? I said, if the owner wants it, then we're going to do it, right? Jerry said, okay, before we take this out into the field for like a real project, pilot project demo, I need 12 months to get you a prototype that we can ship to a customer. And he says, and wherever it goes, it needs to, he says, I need 12 months. And Ben says, okay, you got 3 months. Okay. You don't have 12 months. You got 3 months. He says, and Jerry said, okay, I can do something. I can package this up in 3 months, but the site needs to be at room temperature. We have to drive it there by car. Okay. Put the scanner in its own seat and the electronics in its own seat. I need a Cyra engineer on site. And Ben says, okay, I hear you. He says, but the first demonstration pilot project is in Venezuela. Okay. So obviously not a car ride from San Francisco. Obviously not at room temperature. It's hot and humid. Anyhow, they shipped the scanner and the engineer, and they went to Venezuela, and they got it to work. And they were happy happy campers. The next demo was in Kazakhstan. Okay. So Chevron had just bought some new facilities. They didn't even know what they had. They just wanted to, capture it. Anyhow. So all of that went into what I call the breakthroughs for developing the technology, the hardware, okay, which was a lot. And I need to add here, I know that I had written a series of articles on this whole early days of scanning. I learned about all that stuff after I wrote those articles. So that information is not in the articles. That was interesting. Remember, I said in addition to the hardware, there were challenges on the software side. So the original vision was that they'd take these scan points into CAD and then create the as-built models in CAD. That was their vision. First time they tried to do that, and the scanner was probably at that point doing maybe 30 to 50 points a second. First time they tried to do that, CAD programs, it crashed, right? So there's no way. So they said, okay, what are we going to do about this? So it turned out that there was a professor at the University of California at Berkeley, Dr. Carlo Sequin, Sequin, and he was a professor of CAD and computer graphics software. Okay, so they took the problem over to him and they said, "Here's our problem. What do you think?" And Sequin said, "Don't use CAD software architecture." He said, "You need to use computer graphics software architecture." So that'll be the only thing that can handle that kind of data size. Okay. So for Ben, that was good news and bad news. Okay. The good news was, okay, it looks like there's a path to be able to handle these, point cloud, right, and the data. The bad news was there was no such software like that. So they figured out, well, we're going to have to develop the software ourselves. They hadn't planned on that, right? So the hardware turned out to be a much bigger chore. And then the software, they never thought they were going to have to develop software for it, but they had to develop software. So they did it. They recruited mostly students from Carlo Sequin's classes, right, at Berkeley, that would, work at Cyra to develop the software. And they did it. They developed the software, and the very first software was called CGP, which stood for Computer Graphics Perception. Okay. That was later changed and modified into other software. It's known as Cyclone, and that's like a Cyclone software. But before that, it was called Computer Graphics Perception, or CGP software. And it was all because of this guidance that they got from this professor at Berkeley. And finally, the last challenge was really on the funding side. I talked about a couple of those. I talked about MIT's investment, Chevron's investment, Floor Daniels' investment, and they were Ben Kacyra and his wife Ben and Barbara. They took some money that they got from the sale of their engineering company, Cigna, and they put a fair amount of money into funding Cyra and funding this development. And then over time, they were able to attract some other friends and family and some other investors into it. So they were all big challenges. They got, hardware was a big challenge. Software was a big challenge. Funding and development that was much bigger than they ever anticipated was a big challenge. But the Cyra team, they met all those challenges. If they hadn't met them, I wouldn't be here talking with you right now.
Yes, I think there were a lot of challenges, and it worth it. So this is it. I think there are a lot of points that we can discuss. I think I propose to make other episodes, so we'll stop here.
Okay.
And make other episodes. So just I want to say see you in the next episode.